So for the last lecture of this week, we will look at recursive functions. So recursive functions are typically based on what we call inductive definitions. So in arithmetic, many functions are naturally defined in an inductive way. So let's explain this by some examples. So the first and most common example of a function defined inductively is a factorial function. So we say that 0 factorial is 1. And then we say that n factorial can be obtained from n minus 1 factorial by multiplying by n. So remember that n factorial is nothing but n into n minus 1 into n minus 2, this product all the way down to 1. So what we are observing is that after n, what appears can be rewritten as n minus 1 factorial. So inductively, n minus 1 factorial can be extended to n factorial by multiplying by the value n. So we can also do this for other functions. You may remember, or you may not, that multiplication is actually repeated addition. When I say m times n, I mean m plus m plus m plus m n times. So how do we define this inductively? Well, we say that m times 1 is just m itself, and m times n plus 1 is m plus inductively applying multiplication to n, right? So we could equivalently write this, if you want to be symmetric with the previous case, as m times n is m plus m times n minus 1, right? The same thing. So what you're saying is that you can express m times n in terms of m times n minus 1 and then adding n. Right? So in both these cases, what we have is that we have a base case. So we have like 0 factorial or m plus 1, m times 1, where the value is given to us explicitly. And then we have an inductive step where f of n is defined in terms of f of n minus 1, and in general it can be defined in terms of even more smaller arguments. So one example of that is the Fibonacci series. So if you have seen the Fibonacci series starts with 1, 1, 2, 3, 5 and so on. And this is obtained by taking the previous two values and then adding them. Okay? So the general rule for Fibonacci is that the first value is equal to the second value is equal to 1. And after the second value, Fibonacci of n is Fibonacci of n minus 1 plus Fibonacci of n minus 2. Right? So in general, a recursive or inductive definition can express the value for n in terms of one or more smaller values of the function for smaller inputs. So our interest in inductive definitions is that an inductive definition has a natural representation as a recursive computation. So let us look at factorial. So here is a very simple Python implementation of factorial as it is defined. It takes the value n and says if n is 0, then return 1. Otherwise, return the value n times the computation recursively of factorial n minus 1. Right? So this is very clearly what we said before. We said 0 factorial is 1, and otherwise if n is not 0, n factorial is n times n minus 1 factorial. Right? So this is exactly what we wrote before, directly translated as recursive computation. We can say the same for multiplication. We can say if we want to multiply m by n, if n is 1, we return m. Otherwise, we add m to the result of multiplying m by n minus 1. Right? So again, we had written that before as m times 1 is m, and m times n is m plus m times n minus 1. Right? So if you have an inductive definition, it immediately gives rise to a recursive function which computes the same definition. But the advantage is that we don't have to spend much time arguing that this function is correct, because it directly reflects the inductive definition, the mathematical definition of the function we are trying to compute. Now, what may be less obvious is that we can do the same thing for structures like lists. So a list has an inductive structure. A list can be thought of as being built up from an empty list by adding one element at a time. So we can think of decomposing a list, reversing this step. So we start building a list from an empty list by adding one element at a time. Say we add them to the left. So we add the last element, then we add the second last element, and so on. But conversely, we can say that given a list, we can decompose it by taking, say, the first element and looking at that first element and the remaining list after removing the first element, which has one less element. So this gives us our induction. We have a smaller structure on which we can try to express a function, and then we can combine it with the first element to get the value for the larger thing. Okay? So we will have a base case where the function is defined either for the empty list or for a simple list of size 1. And in the inductive step, f of L will be defined in terms of smaller sublists of L. Again, this is best understood through some simple definitions. Supposing we want to compute the length of a list L. Well, the base case is if the list is empty, it has 0 length. So if L is equal to 0, L is equal to the empty list, we return 0. Otherwise, what we do is we have a list consisting of a number of values. So we pull out this first value and we say it contributes 1 to the length. And now inductively, we compute the length of the rest. Right? So we return 1 plus the length of the slice starting at position 1. So this is an inductive definition of length which is translated into a recursive function. And once again, by just looking at the structure of this function, it's very obvious that it computes the length correctly, because this is exactly how you would define length inductively. Now here is another function which does something similar, except instead of computing the length, it adds up all the numbers, assuming that the list is a list of numbers. So again, if I have no numbers to add, if I have an empty list, then the sum will be 0 because I have nothing to put into the sum. On the other hand, if I do have some numbers to add, well, the sum consists of taking the first value and adding it to the rest. So if I have a list called x1, x2 up to xn, then I'm saying that this is x1 plus the sum of x2 up to xn. Right? So I can get this sum by this recursive or inductive call, and then I just add this value to that. So insertion sort, which we have seen, actually has a very nice inductive definition. If we have a list of size 0 or size 1, it is already sorted, so we don't have to do anything. So this becomes the base case. On the other hand, if we have a list of length 2 or more, we inductively sort the slice from the beginning up to but excluding the last position. So this is the slice from 0 to the length of the list minus 1. Then we take the last position and then, so this should be minus 1. So we take the value at the last position and we insert it into the sorted slice. Right? So we insert the last position into the inductively slotted slice excluding the last position. So here is a recursive definition of insertion sort in Python. So the natural thing in Python or in any other thing would be to say that we want to insert the last position into the result of sorting the sequence up to but excluding the last position. But the way we have written our insertion sort, this function does not return a list. It sorts this thing in place. Right? So this call would not have the correct type, because insert will take a sequence and a position and insert this value at this position to its left. Right? So we write it now as two separate things. So first of all, we have an overall insertion sort which takes a sequence, and it will call this auxiliary function which says sort this sequence up to this position. Right? So isort sorts the slice from 0 up to k minus 1. So what does isort say? Isort checks if it's a base case. If k is 0 or k is 1, if I'm sorting up to the first position, okay, or I'm not sorting anything at all, right, then I will just return the sequence. Right? So this is telling me sort from 0 to k minus 1. So if it is 0, then I have an empty list. If I have 0 to 1, then I have a list of 1 position. It's only if I have 0 to 2 that I have at least 2 elements. And if so, what I do is I sort k minus 1 positions and I insert the last position into this sequence. And what does insert do? Insert does exactly what we did when we did the regular insertion sort. It sets a position variable or name to the last position and walks left and keeps swapping so long as it has not reached the left hand side edge, and so long as it finds something to the left which is strictly bigger than the one that you're looking at now. Right? So this is what we did earlier. And what is new is this part, which is this recursive call. It says sort the sequence up to this position recursively using the same isort, but change the index from k to k minus 1, and then insert the current value into the sequence. So as before, let us run this in Python. So here is the code isort rec py, which contains this recursive implementation of insertion sort. So if I now import this, and then as before, if we say L is a range of 500 values, say in descending order, then if we apply insertion sort to this, then L produces the ascending order 1 to 500. So last time we said that for n squared sort we should look at larger values. So supposing we take range 1000. Okay. Now if we take range 1000, then something surprising happens. Okay. So we get an error message from Python saying that it could not sort this because it reached something called the maximum recursion depth. So what happens when we make a recursive call is that the current function is suspended. So we try to sort something of length 1000, right? So it will try to insert the 1000th element into the result of sorting the first 999. So we suspend the first call and try to sort 999. This in turn will try to insert a 999th element into the sorting the first 998. So it will suspend that and try to sort the first 998. So at each time we make a recursive call, the current function is suspended and a new function is started. So this is called the depth of the recursion. How many functions have we suspended while we are doing this process? Now, unlike some other languages, Python imposes a limit on this, and the limit, as we can see, is clearly less than 1000 because we are not able to sort a list of 1000 using this particular mechanism. So how do we get around this? Well, first of all, let's try and see what this limit is, right? So we know that we can't sort 1000, but we could sort 500. So can we sort 750, for example? It turns out that we can sort 750. It will turn out that, for instance, we can sort 900, right? So we can actually find this limit by doing what we did earlier, binary search. We can keep halving, although I did not strictly halve. After 750, I know it fails at 1000. It doesn't fail at 750. I should have tried 875. But I will spare you this binary search, and I can show you that if I use 997, right, then it will work. But if I use 998, then it will fail, right? So somewhere around 998 is the recursion limit that Python uses by default. Now, fortunately, there is a way to get around this. So you can set this recursion limit, and the way you do it is the following. You first have to import a bunch of functions which are called system dependent functions by saying import sys, and then in sys there is a function called set recursion limit, and we can set this to some value bigger than this, say 10,000, right? And now if we, for instance, ask it to sort a list of 1000, then it doesn't give this error. Same way I could even say 5000, because 5000 will also only create the same kind of limit because it's well under 10,000. Remember that in this we are basically doing recursion exactly the number of times as there are elements, because we keep inserting, and each insertion requires us to recursively sort the things to its left, and that's why we get this stack of nested recursions. But the thing to remember is that by default, Python has an upper bound on the number of nested recursions which is less than 1000. If you want to change it, you can by setting this recursion limit explicitly, but Python doesn't allow you to set it to an unbounded value. You must give it an upper bound, right? So you can't say let recursion run as long as it needs to. You have to have an estimate on how much the recursion will actually take on the inputs you are giving, so that you can set this bound explicitly. Now, the reason that Python does this is because it wants to be able to terminate a recursive computation in case you have made a mistake. A very common mistake with recursive computations, it's a bit like we said for while loops. If we do never make the condition false, a while loop will execute forever. Same way, if we don't set the base case correctly, then a recursive computation can also go on forever. So the way that Python stops this and forces you to go and examine the code is by having a recursion limit saying beyond a certain depth, it will refuse to execute the code. Right? So what we have seen is that we have this recursion limit, and we can raise it manually by importing the sys module and setting the set recursion limit function inside sys. So how would we analyze the complexity of recursive insertion sort? So as before, we use T of n to denote the time it takes to run insertion sort on an input of length n. So insertion sort at the highest level consists of two steps. We first have to sort the initial slice of length n minus 1, and by definition this will take time T of n minus 1. And then we need n minus 1 steps in the worst case to insert the last position into the sorted slice. So this gives rise to what we call a recurrence. We saw this when we were looking at how to analyze binary search, which was also a recursive algorithm. We have that Tn in general is n minus 1 plus T of n minus 1, and T of 1 when we come to the base case is 1. So as with the binary search, we can solve this by expanding or unwinding the recurrence. So we have T of n is n minus 1 plus Tn minus 1. So if we take Tn minus 1 and apply the same definition, we get n minus 2 plus Tn minus 2. Then we take Tn minus 2 and apply the same definition, we get n minus 3 and Tn minus 3. And this will keep going on until we get T of n minus k is equal to T of 1. So in other words, when k becomes n after n steps, we will have 1. So we will have n minus 1 plus n minus 2 down to 1, which is the same thing we had for the iterative version of insertion sort, n into n minus 1 by 2, and this is order n squared. So we have seen two order n squared sorting algorithms, both of which are very natural, intuitive algorithms which we do by hand when we are given sorting tasks to perform. Selection sort and insertion sort. We have also seen that both of these will not work in general if we have large values of n, and not even so large if we have values of n over 5000. But we also saw in the previous two lectures that insertion sort is actually slightly better than selection sort, because selection sort, the worst case is always present because we always have to scan the entire slice in order to find the minimum element to move into the correct position. Whereas insertion sort will stop as soon as it finds something which is in the correct order. So if we have a list which is already sorted, then insertion sort will actually work much better than n squared. But we can't rely on this, and anyway we are counting worst case complexity. So we have to take the fact that both of these will in general not work very well for lists larger than 5000 elements. What we will see next week is that there are substantially more efficient sorting algorithms which will allow us to sort much larger lists than we can sort using selection sort or insertion sort.